All right, so last time we had class on Tuesday, okay, we looked at section 8.4 about similar triangles. We saw one way to prove triangles similar. Does anybody remember the name of it? It was 2 letters and then a postulate. Or maybe 2 letters and then a word and then a postulate. Yep.
Angle, symmetry,
Similarity.
similarity.
Yeah, angle, similarity, postulate. Good. Okay, well, there's 2 other ways we can prove triangles congruent without necessarily knowing all the angles, okay, or 2 of the angles. We don't even need to know 2. Okay. If we have some information about sides, we could use that instead. Okay, and the first one is side similarity theorem. Okay. Does anybody recognize this a little bit?
Yeah, we did that.
Kind of looks like something we did earlier, right?
Yeah.
Earlier we did side congruence theorem, okay, proving 2 triangles were congruent. Well, this is side similarity theorem, so it's a little different. Okay. In side congruence theorem, we had to show that 3 sides in one triangle were congruent to 3 sides in another triangle. Okay. That's what we did before. Okay. Let's see what this is. This one is all about being proportional, not congruent. Okay, so it says, if the lengths of corresponding sides of 2 triangles are proportional, then the triangles are similar. Right, let me show you an example. Okay, in this theorem, we're not going to know anything about the angles. Okay, we don't need to. Let's take this triangle, group everything together. Let's make a copy of it. And paste it. And make it a little larger. Okay, what you do need, though, to use side similarity is you need to know the lengths of every side. So let's say this was 2. This was 4. This was 3, and that was 6. And let's make this one 4.5 and 9. This is an example of where we could use side similarity theorem to prove these triangles are similar. Okay? What's the scale factor here from the small triangle to the big one?
2.
It's a scale factor of 2. Okay? Basically, if you compare, and I'll do it in different colors so we can make the comparison. Okay, if you compare the red sides versus comparing the green sides versus comparing the black sides, they're all going to come out to 2. Okay, they're all going to come out to the same fraction, same ratio when you divide it. So we'd have 2 to 4 for the red sides, 3 over 6, and 4.5 over 9. So if you reduce it, this comes out to 1/2. 3 over 6 is 1/2. 4.5 over 9 is 1/2. Okay, so they're all in the same ratio. Ratio of 1. I think Denver, you had said the big triangle to the small triangle. That's 2 to 1.
Yeah.
So small triangle to big triangle is 1 to 2. Yeah. But depending on, I think I asked the question, how much bigger is the big one? I think I said it that way. So that's fine. Okay. But the idea is you compare corresponding sides. They all come out to the same number when you divide them. Okay. So these triangles are similar. You don't have to know anything about the angles. But now that you proved they're similar, using side similarity, you know this angle and this angle are the same. Now you also know this angle and this angle are the same. And that angle are the same. Just by using side similarity. Okay. All right, and there's one other way we can prove triangles similar. Okay, and we've seen this before too, side angle side. But we did side angle side congruence. This is side angle side similarity. In fact, I think there's a question on your pre-mid final that 10 questions or 12 questions we do in September. We did it in January. We're going to do it again in June. There's a question about a similarity theorem on there. Okay, and this one says, you got to know, in this one, you don't have to know all the sides. You got to know 2 of the sides and 1 of the angles. And it says, if an angle in one triangle is congruent to an angle in a second triangle, and the lengths of the sides including that angle, in other words, it's the sides that make up the angle. Okay. If those sides are proportional, then the triangles are similar. Okay, here's an example of that. Let's just take and make a triangle. Okay, take that up. Let's group it, make a copy of it. Yeah. All right, so I just made a smaller version of it. And let's label some stuff here that would allow us to use side, angle, side. I've got to label 2 sides and 1 angle. Okay, let's say this is 100 degrees. This is 100 degrees. Let's label the top side 12. Okay, let's make that 4. Let's make this one 9. And what do you think this other one would have to be if they're going to be proportional?
3.
Yeah, it would have to be 3. All right. Actually, sorry, I messed you up. Instead of labeling the top one, keep the 9 and the 3. That's fine. We got to label this one. Let's make this one. You know what? Let's just keep it as 12 because the arithmetic is easy to do, even if it doesn't look to scale. That's okay. This is where you could use side, angle, side. You know an angle, and you know the 2 sides that make up the angle. Okay, let's check the proportions. Okay, corresponding sides are 9 and 3, 12 and 4. If you reduce it, 9 divided by 3 is 3. 12 divided by 4 is 3. So the sides are proportional. And the other thing you got to check is that the angle's the same. 100, 100. Yep. So these 2 triangles are similar. The included sides, included means the ones that make up the angle, are proportional, and the angles are congruent. Okay. Any question on side, angle, side similarity? Okay, so now you've got 3 ways to prove triangles similar. Angle, angle similarity, side, side, side similarity, side, angle, side similarity. All right, and I think that's pretty much all the main ways that we'll have, those 3. All right, so I'm going to take a second to look at these triangles and see if I can figure out which ones are similar. Well, which theorem do we have to use here to prove these are similar? We're missing information that wouldn't allow us to use some of the other theorems I've taught you. Yeah? You're going to have to go with side, side, side. You don't know any of the angles, so we can't do anything with any of the angles. All right, so take a second. Just look at them. It might be tricky because they could be turned. So you might have to visualize turning one of these to figure out corresponding sides. Let's take a second and look at that. All right, so after looking at that a little bit, Ian thinks that the top 2 triangles are similar. All right, so Ian, can you tell me which 2 sides are you going to compare that are proportional?
ED and AB.
All right, he's going to compare, all right, ED. Okay. ED to which one?
BA.
BA, okay. That's one of them. Can you name the other 2 pairs?
AC, DF.
Okay, just make sure we're consistent. So you started with ED, we got to stick with that one first, that one second now. So which one you want to put in the top here?
Wait, what? DF.
DF, okay.
CS.
So we got DF and CA, and what else?
And then FE, CB.
FE and CB. So if we fill in all the numbers and they come out the same in each fraction, those two triangles are similar by side, side, side. Okay. ED is 4. Let's see. BA is 6. Okay. DF is 8. And CA is 12. Okay. FE is 6. And CB is 9. Okay, let's reduce them. Okay. 2 goes into each of those, so we can write it as 2/3. 4 goes into 8 and 12, that's 2/3. 3 goes into 6, and 3 goes into 9, 2/3. Perfect. Okay, so those two triangles on top are similar. All right, so now when we write it, we just want to be careful how we do it. So Ian, could you give me the ordering of which triangle is similar to which?
Triangle EDF and is similar to BAC.
All right, so triangle, you said EDF.
Yep.
Okay, so once he picks the 3 letters on the right, he can do any order he wants, but now he's going to be very careful about how he names them on the left. So go ahead. Would you say EDF and?
BAC.
Yep, BAC. Perfect. All right, so basically, all you have to do is try to come up with a system or a pattern for figuring out the ordering. All right, so E, D, F. Okay, so ED, that's the shortest side. Okay, so go to this triangle and figure out, all right, what 2 letters make up the shortest side? BA. We just got to make sure we put them in the right order. Yeah. So we got BA, all right, and then look at the next 2 letters. DF. DF, that's the longest side. So we got to go over here, look at what letters make up the longest side. That's AC. AC is the longest side. All right, so you just have to be careful how you name it. You could have also done, another ordering would have been D, E, F, A, B, C. Could have done it that way. All right. And if we look, I don't think there's anything else that's similar. Triangle DEF and GHJ. Those aren't similar. Okay. So if we know that this one and this one are not similar, do we even need to check if that one is similar to that one? No. Because if the 2 on top are similar, and one of them is not similar to the one on the bottom, then the other one on top isn't similar to the one on the bottom, because it's in the same proportions as the other one on top. All right? So once you check that, you're basically all set. Okay, so that's good. So we got our answer. Okay, next one, a little bit more calculation based. Okay. Actually, no, this one's not calculation. We're just proving the 2 sides are, using sides to prove that triangles are similar. All right, so my goal is to prove that RST is similar to PSQ. Prove the red and the green triangles congruent. Okay, we don't have to write a formal proof. We're just going to write, we'll write the steps and then write down what theorem you used. Okay, so yep, Connor, what are you thinking?
The total length of ES is 20.
Okay, the total length of which side?
TS.
TS. Yep, that's 20. Okay.
So
let's write that down. So I'm just going to write down information for now. So TS is 20. What else do you know?
RS is 16.
16. Okay, those are a couple numbers we're going to use because those are the sides of the bigger triangle. Now we got to try to see if we can set up a proportion that would allow us to use one of our theorems.
S is congruent to itself.
Okay, we have an angle that's congruent to itself. Okay, so angle S is congruent to angle S. Okay, let's write that down because that's going to be one of the statements we need to say when we do our similarity theorem. Angle S is congruent to angle S because of, what's that word again? Why is it congruent to itself? Reflexive. Okay, so that's one. Gives us an angle. So right away, we're probably not thinking side, side, side. Okay, we're thinking either angle-angle similarity or side-angle-side similarity. Well, I don't think we can do angle-angle because I don't know that SPQ and SRT, they're corresponding, but I don't know if they're congruent. If these were parallel lines, now we could do all kinds of things. We'd have parallel lines cut by a transversal, corresponding angles are congruent, we're done. But we don't know they're parallel. Okay? So what could I set up here for a proportion? I want to set something up to see if the sides of the big triangle and the small triangle are proportional.
20 to 5.
Okay, so he's saying 20 to 5. Okay, so let's say next, set up a proportion. Maybe we should even write down what we're going to set up, and then we'll plug the numbers in. So we're going to compare the right side of the big triangle. Right side, big. And he compared it to right side, small. Okay? Right side, small. Well, then we're going to have to compare it to left side big over left side small. Okay? And see if it comes out proportional. So left side of the big over left side small. It's important that you set your proportion up the same on each side. Big over small, big over small. If you wanted to flip it, you could do small over big, but then you got to flip the other side, small over big. Just set it up the same way. All right, so Connor, what did you say the right side of the big triangle is?
20.
Yep, we got that earlier, 20. And the small side of the green triangle?
5.
Or the right side of the small triangle? Sorry, 5. Okay, we're hoping this comes out equal. Jacob, what's the left side of the big triangle?
Twelve.
12 is part of a quadrilateral shape, so we need the whole side. We need the 12 plus the top part. 16. Over. James, what's the small side of the left triangle?
That's 4.
That's 4. Okay. Brian, if I do 20 divided by 5, what do I get?
4.
And 16 divided by 4?
4.
4. Okay. So we just showed that two pairs of sides are proportional. We showed that we had a congruent angle by the reflexive property. So these triangles are similar by side angle side. So we have two sides proportional and an angle between, I use the word included, but the angle between the sides, congruent. So, side angle side, make sure you say similarity theorem, not congruence. So by side angle side, similarity theorem, these triangles are similar. Okay, so we use side angle side. Any question on that? So it's not quite as formal. We could write this as a statement reason, put the two columns. We're just not doing it this time. Okay. All right, so that's that one. Okay, now, actually, let me go back to that for 1 sec. Now that we know these triangles are similar, we could say that this angle corresponds to this angle. And then we could say by the corresponding angle's converse, if we wanted to, these lines are now parallel. If you have two lines cut by a transversal, so the corresponding angles are congruent, you must have parallel lines. So they could ask us to show that, which would be a very easy next step once you have corresponding angles. As long as you remember all those theorems. That's the part about geometry. You've got to remember all the old theorems. Okay, so in the figure below, they tell us that, let's label this, AC is 6, AD is 10. Okay, so, yeah, you know what? I think labeling it, it's going to be hard. It's going to look a little confusing, so might hold off on that. AC is 6, AD is 10. Okay, BC is 9, and then BE is 15. Prove these triangles are congruent. Does anybody have a thought by looking at it which theorem we might use? Angle-angle similarity, side-angle side, or side-side-side? What do you think? Connor, which one?
I would think angle-angle similarity because we have E, C, D, and and B, C, A. Now, those are vertical angles.
Yep, we do have a pair of vertical angles, so let's start with that.
And then we could use angle D and angle A are congruent because of, what's it called?
Which angles, A and D?
Yeah.
I don't think we know that those are congruent. If we had parallel lines, again, if these were parallel lines cut by a transversal, we would have some kind of maybe alternate interior angles or something like that. But we don't know that we have parallel lines yet. If they're similar, then we do. But we don't know that yet. All right, but I like the first part of what you said. Angle ACB is congruent to DCE. Because they are vertical angles. Okay, now I think we're going to have to use some of those side numbers. Okay, they wouldn't usually give us all those lengths of sides if we weren't going to use them somehow. So what can I figure out here? Okay, look at what they've given me. Let's look at, let me try to write it in the best I can. AC is 6. Okay, AD, this is 10. Maybe that's not too confusing. What else do you know there? If you know AC and you know AD, you know something else.
DC.
Yeah, what would DC be?
Direct current.
Direct current, yes. No. How long would DC be? Yeah, DC would be 4. Now, we know two sides in the triangle, we can compare them. Okay? Let's do the same thing on the other side first. BC is 9, but the whole thing, put it down here, the whole thing is 15. From there to there is 15. So how long is EC? Oh, Selena? 6. Good. So this is 6. Okay. So I did it in different colors so you could try to maybe keep keep it straight a little bit. Anybody see a proportion that we could set up to show if those are similar? So remember, ACB, this is one triangle, and DCE, this is the other.
Yeah.
So why don't we set it up like we did before? Big side of one triangle, to small side. Big side of the other triangle to small side. Okay, that's one way you could do it. So let's do next. Okay, how you set up the proportion is up to you. There's a lot of different ways you could do it. Okay, but let's start with big side of triangle ACB. Okay, and let's compare that to the smaller side in triangle ACB. So big to small. And then let's compare that to the big side of triangle DCE. And by big side, I mean the bigger number of the two that we have over small side. Triangle DCE. Hopefully those come out proportional. If they do, then we're good. Rose, what's the bigger side in triangle ACB?
The bigger side.
Yeah, how long is it?
BB.
It's 9. Yep. So the bigger side is 9. Okay, in Denver, what about the smaller side?
4.
In triangle ACB? 6. Okay, 6 is the smaller. So we're hoping for something that comes out in a ratio of 3 to 2 when we reduce it. Okay, what's the big side in triangle DCE? Katrina?
6.
Yep, the bigger side is 6 over the smaller side is 4. Okay. Do both of those reduce to the same thing? I think, listen. Yeah, these both reduce to 3 over 2. So we get 3 over 2 equals 3 over 2. Okay, so now we have a pair of proportional sides. And the angle between them is congruent. And angle between is congruent in each triangle. So by what theorem have we proven these triangles similar?
No side angle. No side angle side.
By side angle side. Pair of sides proportional, angle between them congruent. So by side angle side, instead of listing it out, I'm just going to say our triangles are congruent. Sorry, not congruent, similar. Now that we know they're similar, there's all kinds of other things we could do, but that's all they wanted. Yeah.
Can you scroll back up a number?
Mhm.
Technically, since we know that DCE and ACB.
So DCE, yeah, that's that vertical angle on the left, and which
Since
one?
we have both vertical angles, wouldn't that mean DCB, that one there,
Yep.
and ACB are vertical, and that means we
Well,
have
this
vertical
one-
lines?
You mean ACE?
Yeah.
Like that? Yep, these are angles that are outside the triangle, though.
Right, but wouldn't that also mean we have parallel lines?
No. No. The only way you can, well, there's 3 or 4 ways you can prove lines are parallel. 1, corresponding angles could be congruent. 2, alternate interior angles could be congruent. 3, consecutive interior angles could be supplementary. Might be a 4th way too, but we don't have any of those that would apply here. All we have is these vertical angles. What you'd really need is this and that. You would have to been given that. Or you could have been given this and that. And then I think we could have done something. But unless they're going to tell me a little bit more about these other angles, not just these vertical ones,
Okay.
I'm pretty much
Understand now, I see.
stuck doing it that way. Yep. But now this is true. Now all these angles are congruent. Okay. All right. The other thing that you can use similar triangles for, kind of something more practical, is to measure distances. Okay. Now when I teach something like this in trig, we actually go outside. We measure an angle to like either the roof or a goalpost or any object we want to get the height of. And we can measure that angle with a transit that has a laser on it. Or we can measure it with like a tool we can make like use a protractor, have a string hang from it with a weight, and put a straw on top of the protractor, and you look through the straw, and as you turn the straw, what happens is the string always points down, but the protractor pivots, and it tells you the angle that you're tilting it at, so we can get the angle to an object. We're going to do it a little differently. We're not going to use trig to measure distances. We're going to do it with a similar triangle and a mirror on the ground. Right? So I'll show you the example, and this is something you could actually try, and this would work. This is just like a real life kind of thing. Yeah?
What's the tool that you use, like when a rocket goes up and it reaches like the apex? Do you know what that's called?
To measure, what are you measuring? Like the speed of it?
I don't know. Just like when it reaches it, you like pull a trigger and it like marks something on this thing.
I'm not sure.
Okay.
I'm not sure. I know a transit is generally something used by surveyors. If you've anybody ever seen those guys on the side of the road with the tripod set up, and they're looking at something, and then further down the road there's like another tripod.
Yeah.
You know what I mean? They're surveying property. Okay, people get their properties measured all the time, or roads. Sometimes they're grading things, make sure water runs off correctly. So they're measuring distances and angles a little differently than we're going to do right here. But let's look at it. Okay. This problem is in your book. Okay, if you just want to reference it, it's on page 491. So you don't have to write it down. It's example 5 in the book. Okay, and it says you're at an indoor climbing wall, and you want to estimate the height of the wall. Okay, you want to estimate the height of the wall. So what they're suggesting you try to do is place a mirror on the floor 85 feet away from the base of the wall. Now, it doesn't have to be 85 feet. The point is that if you're placing the mirror on the ground, it's very easy to measure the distance on the ground. It's flat. Measuring the distance up the wall, that's, let's say you had a wall that was like 400 or 500 feet high, a really, really high wall. That would be hard to measure. Okay? But the ground, even if it's very, very long distance, easy to measure. Okay? So you're going to put a mirror on the floor 85 feet away from the base of the wall, and then you're going to walk backward. Okay? You're going to look at the mirror, and you're going to continue walking backwards until you see the top of the wall centered in your mirror on the ground. All right? So you keep backing up, look at the mirror, and then finally, in the mirror, you'll see the top of the wall. Okay? And then when you back up, you have to measure how far away are you from the mirror. So in this case, the person was 6.5 feet away from the mirror. And the person is, let's assume that their eyes are basically the top of their head. All right? I know there's a little bit more distance there, but we're going to measure it from their eyes. Okay? 5 feet above the ground. Okay? You could basically use your height. It'd be a little off, but if you used your height, that would be okay. So your eyes are 5 feet above the ground. Estimate the height of the wall. So this is good. We have a description of what's happening. But what do you think would be even more helpful than this entire description in words?
Go to the owner and see.
Ask the owner what the height of the wall is. That's a good option. If the owner's not there, what else? What else could we do with all of this, all these words in this description? Yeah, we should draw it out. Hopefully we're going to draw it out, and our goal is to draw some triangles, okay? And figure out somehow we should have similar triangles here. Okay, so what I started to do was sketch it. Okay, we have a mirror on the ground right there. Okay, here's the top of the rock wall, okay, over there. And now it says, we've got to put in some numbers. There's a mirror on the ground 85 feet from the base of the wall. Okay. So this distance is 85 feet. Okay, next it says you're going to walk backwards 6.5 feet. Okay, so if you walk backwards to about this point right here, there you are. This distance is 6.5 feet. Okay, from there to there. Now it also says that your eyes are 5 feet off the ground. Okay, so this is 5 feet. And our goal is to find the height of the mountain. Okay, so let's draw a triangle.
How do you determine where the mirror goes?
You can put the mirror wherever you want. Doesn't matter. As long as you know how far the mirror is from the base of the wall. It may change how far you have to back up. For example, if you put, I'd have to think it through, but if you put the mirror really, really, really close, you probably wouldn't have to back, let me think. If you put the mirror like right here, and you're standing here, okay, you might not have to back up from the mirror as far. I don't know, I'd have to think the angle through. Because basically what happens is, you're looking into the mirror, like this, and what you're going to see when you look in that spot reflected is, let's get this. Okay? So you can almost imagine that like a laser beam. If you had a laser beam pointing down at that right there, it would bounce up and hit the top of the mountain. Okay? And now what we're trying to find is the height. Okay? And basically we can make a triangle right there. Okay, now one thing you'd have to know about mirrors is that when something bounces off of the mirror, the angle that it bounces in at is the same as the angle it bounces out at, okay, for a flat mirror. Okay? It's like if you took a ball that was really bouncy and you threw it at the floor, whatever angle it hit the floor at, it's going to bounce back up at that same angle. So these two angles are the same. Now, when you measure the height of something, what do you know about the angle between the height and the ground?
It's a right angle.
Yeah, this is a right angle.
What if the ground's tilted?
It's a right angle. We're going to assume nice and flat. Nice and flat. Keep it simple. But it could be wavy or not flat. Okay. Do I have similar triangles there?
Not yet.
I do.
Yeah.
What's the reason? Yeah. Angle similarity. Okay. The angle by the mirror and the right angle. So now I have similar triangles. Now we can set up a proportion and solve for h, which is going to be the height of the rock wall. Anyone think they could tell me a proportion to solve for h? Just keep it set up consistently. Sarah?
6.5 over 85.
Yep.
5 over 8.
Yep, that'll work. So we've got the short base over long base, the shorter height over the longer height. As long as you set it up consistently, cross multiply. So 5 times 85 equals 6.5 each. So we get 425. And what's my last step?
Divide.
Yep, divide by
6.5.
6.5, 6.5. Okay, once we do that out, we're going to know the height. The height of the wall, it's about 65.4 feet. Yep, the book rounds it to 65. Okay, but 65.4 feet. Okay, so that's one way you could go and actually do something like that outside. You could get the height of something. Again, this assumes that where you're standing and where your object is, you're at the same height, same altitude. Okay? If you were up much higher, like on a hill, and you're trying to find the height of a tree, but the tree is much lower, the base of it, you'd have to take that into account.
They should do it. Trying to find the height of the school.
Okay, and the last one we'll do is another similar word problem, except this time we're going to find the width of a river. Okay? The bottom line, if you can figure out how to set up your similar triangles, that's the whole problem. Okay, so what a surveyor does is they go out, okay, and they set up their tripod, okay, on one side of the river, and they measure some distances from where they're standing to the river, okay, and a few other distances that would be easy to measure because they're all on land. Okay, so those are the easy ones, the 12, the 9, and the 63. What we really want to know is RQ. Okay, let's call that, that's X.
That's what I'm going to see.
Yeah, so I'll try and make it a little thicker maybe.
Higher line.
Is that better?
I know I have.
Okay, so we're trying to find X, the width across the river. Well, we're going to set up a proportion. The first thing we have to do is prove, do we have similar triangles here?
Yes. Well, no.
Okay, so I see a right angle and a right angle. That's good.
And then the vertical angles.
Yeah, we have vertical angles. Okay, this one. Let me fix that. And that one. Okay, those are vertical angles. So by angle similarity, we do have similar triangles. Now we can set up a proportion to find X. Okay, so to finish up, anybody think they can tell me what's the proportion we could use to find X? Yep.
63 to 9 and
So 63, okay, over 9. So that's two horizontals. You compared the bigger to smaller. Yep.
and X to 12.
And then that side of the triangle that goes across the river compared to this height, these are both the verticals. The bigger vertical, the smaller vertical. So when we cross multiply, it's 12 times 63 divided by 9. Let's see what we get. So we get 84 feet. Or 84, yeah, these are all in feet. I didn't put that, but
What's the ratio?
okay.
We would just have this one.
Yep, that's it. Any question on that? So in real life, if you can set up similar triangles, whether you're surveying something or you want to measure the height of something, just like we did, you could do this and actually measure distances that might be kind of hard to measure otherwise. Hey, any questions on similar triangles? All right, so next time we'll talk more about some more proportions and other special things that happen in similar triangles. We'll tie in parallel sides, but we'll look at that next academic Monday. All right, so the homework, okay, it's in section 8.5. It's page 492. 6 to 15 all, 19 to 25 all, and 28 and 33.